Again, good afternoon to all. The topic for this afternoon will be the basics of BJTs or Bipolar Junction Transistors. So, isbasan ako. Bipolar Junction Transistors. BJTs. The BJT is just one type of transistors that is commonly used nowadays. The other one is the FET or field effect transistor. Pero siguro, medyo taod-taod pa ta nato ni topic ng FET. After pa nga masabtan ginatoon sa ang BJT ug iyang mga applications. So, transistors. Before transistors were invented, the world used devices that were called as vacuum tubes. Okay? So, dili na kayo ni malagwala gid. Anam siguro, no? Apong siguro yung mga gazelle o vacuum tubes, pero not as common as transistors. Okay? So, in terms of operation, application, tanan nga mabuhat sa vacuum tube, mabuhat sa transistor and vice versa. Tanan nga mabuhat sa transistor, mabuhat sa vacuum tube. Okay? Because there are only two general categories of their applications, both the vacuum tubes and transistors. They are used mainly for either for amplification or for switching. And so far as I know, nothing more, nothing less than that. All the other applications of transistors or even vacuum tubes, if napay mga numerous ng applications out there, either subset lang siya sa pag-amplify or pag-switch. So one of the main disadvantage of vacuum tubes as compared to transistors, disadvantage is that vacuum tubes are very bulky, no? Bulky. Oops. And they're power inefficient. Large amounts of the power na iyang makonsume is iyahang i-transform into heat, no? And light. Siga man ni siya. Dili na sa iyahang pag-amplify or pag-channel sa power padulong sa load kay switch man siya. So dili na mapadulong dito but mapadulong na sa iyang self. So it's very inefficient, it's bulky. One common size of vacuum tubes is it is comparable to an incandescent lamp, no, or light bulb. Try to imagine na lang, light bulb. Tanan man siya tanay light bulb sa balay. So, iyan nakadako kung iyan nakadakong light bulb, more or less iyan na pud kadako ang vacuum tube. Okay? Imagine mas nato sa atong hand sa kadako. So, computers before, 1930s to 1950s were mainly made, ilang mga processors were made with vacuum tubes. Okay? So, dagko gigay sila. Dali pag sila mo, another disadvantage po dahil is, dali lang sila mo guba, no? they would easily break down. So, i-replace na po ng part. Yan na. So, comparing computers now that are made of transistors and imagining if they are made with vacuum tubes, ang atong mga fastest processors karon, pila ba ang number of transistors sa ilang sulod, no? Ang i9 sa Intel, pila ba? Intel i9. How many transistors does Intel i9 have? Dahil mga approximately 290 million transistors ang Intel i9. Di din eh. Ay lagi? Oo, sakto. Di ko sure kung i9 bagid na yung diri sa Google. Sa Google naman eh. Sa na dili ni siya dili ni 290 million. Tingnan, magamay naman na siya. Wala may data sa i9 nga dali makita. Core i7 na lang. Naday 3 billion transistors ang Core i7 sa Intel, no? So imagine if ang vacuum tube is the same size as a light bulb, no? Magyana man ang vacuum tube, tulo lang kabukihang terminal sa ubos. Imagine 3 billion of that, no? Imagine 3 billion of these guys. Kung sa kadako nga building ang kinanglan i-build para maka-house og 3 billion ka vacuum tubes to perform the same processes that an Intel Core i7 could perform. So, try to imagine na lang, no? But, ang atong Core i7, pila ba ang physical dimensions? Okay. Nasa mga 4x4. 4 inch by 4 inch ba? 4 inches by 4.6 inches na. Muna ang size sa atong kuan, be? Kung i-draw to scale na to, pila ba? Mga 4 inch na ba ni? 4. Roughly, ingani. No? Roughly, ingani kadako ang i7 nga processor. And these contain 3 billion transistors. Yan kadako nga kuan. Processor, di ba? So, kana alone is the main reason why we could not observe anymore usage of vacuum tubes sa any piece of technology nga exist today. So, ang mga transistors either made from BJT ra gyud or FET. For more, for more detail regarding what vacuum tubes are, pwede naman mo mag-view any YouTube mga video for that. But to tell you frankly, mas more useful nowadays ang FET, no? Kaysa sa BJT, especially with regard to digital electronics, no? Digital applications. Kaning transistors nga kung what the Core i7 is made of, those are CMOS, no? CMOS transistors. And CMOS siya because short na siya for C MOSFET. So, gitangtang lang nila ang FET. Or FET na siya, no? FET ng CMOS, not BJT. So, even though digital electronics today mainly use FETs, pero for us to get an intuition on how transistors in general work, mas magsugod ta sa investigate. Magsugod ta by investigating BJTs. So, BJT gyapon ta mo una. Bisan pa nga FET ang mostly ginagamit karon. Okay? Mas dali magudtuan, mas dali ma-appreciate, no? Mas dali ma-appreciate ang transistors kung first na naka-understand what BJTs are and how they work. Kaysa sa mo diretso ta sa FET. No? So that is our main topic for this afternoon. Okay, BJTs. So the BJT has 3 regions called the emitter, the base, and the collector. Unlike the diode, which has only 2 regions, the P region and the N region, we could create a transistor by adding a third region. Either another N or either another P. Hence, may 2 types of BJTs. The NPN and the PNP BJTs. So, muna ang mga terminals niya. This is the collector, the base, and the emitter. Same gyapon sa PNP. The collector, the base, and the emitter. So, asa sa differ sa ilahang physical na construction, what they're made of. Of course, ang PNP is made of 3 layers of a P-type material, an N-type material, and another P-type material. So, na-sandwich in between ng N. Whereas sa NPN is na-sandwich in between ng P. Okay? So, palang other differences. Okay. Later na lang, basig kuan na ako, no? Cover ba. Yet, mostly used food ang NPN kaysa sa PNP. Okay? So, for the most part, unless otherwise stated, it is assumed that we are using NPN transistors. And actually, maklaro naman po sa ihang symbol kung NPN ba siya or PNP. Naman sila difference. Pero, putang lang nila sa inyong reminder na mas common na itong magamit ang NPN kaysa PNP. Now, there's a reason for that. It's because ang majority carrier for NPN, if you remember, majority carrier for NPN is electrons, right? And it's conventional na knowing, no, conventional na current flow is ang electrons baya. So, that's the reason why most ng mga BJTs ginagamit kay NPN kaysa sa PNP. Because we're following the electron flow, the flow of electrons for electrical current. So the base is a thin, lightly doped region compared to the heavily doped emitter and moderately doped collector. So ang pinaka-heavily doped is ang emitter. So if the emitter is the heavily doped na region and Kung N siya, so again, majority carry ka electron. So most of the electrons nag-flow is magikan sa iyaha. No? Tungod sa heavily doped na emitter region. Now, this is not drawn to scale. Okay? Dili nga ni ang ratio sa thickness or sa dimension sa P, sa N, o sa P. Both sa P, sa emitter, o sa collector. So, dili nga ni, no? Dili nga ni ka equal. Okay? Mas baga actually ang I think ang emitter, no? Mas baga na siya. Then gamma nipis sa gid kayo ni ang base, no? Nipis sa kayo na siya. Operation. Before that, dala. Later na lang tong second slide, dito sa third slide. BJT currents. The direction of conventional current is in the direction of the arrow on the emitter terminal. So these are the two schematic symbols for transistor. This is for the NPN and this is for the PNP. Please notice kung asa sa differ ang arrow na nasa sulod. Okay? Para dali ta makahinumdum, kung asa nga terminal ang arrow, just like this one, for sure, mo ni ang emitter. Okay? Kung asa ang arrow, mo na ang emitter. Kaya usay, dili mo na i-draw og ingani nga pamaagi. Maybe, i-draw ang transistor in this way. No? So again, kung asang arrow, dito ang emitter. Kung asa ning vertical line, mo na ang base. And the terminal that's left is ang collector. Okay? So same put here. So mo na ang collector, mo na ang base. Base because na dire, no? And mo pa siyang nasa tunga, no? Basta kay nasa tunga, ang base gina siya. So this is PNP because ang arrow is pasulod. Okay? So pasulod ang arrow. Okay? PNP na siya. And basta pagawas ganing arrow, or if the arrow is going towards the emitter, NPN na siya. So, i-memorize na ninyo. Now, mo ni atong pirmi gamiton nga symbol for the BJT. The symbol for the NPN. Notice the current directions. So, we have three currents involved. We have IC, or the collector current, IB, the base current, and IE, the emitter current. Pwede na ito ma-model ang BJT as of this point as a node, no? Dili siya exactly like node sa tulo ka wires, no? Kita mo to sa physical construction earlier, nga layer man siya. Pero we could model it as such, no? Nga mar siya node ang atong transistor. So that we could create our first characteristic of our BJT. The relationship of the currents. Based ani, unsa ang gapasulod ug unsa ang gapagawas. Ang gapasulod is ang IB, ang og IC. And ang gapagawas is IE. So we have a relationship then of IE and IC and IB, which is IE is the sum of IC and IB. Okay? This is equation number 1. So, memorize na natin niya. There are only four equations or formulas nga dapat gid nato memorization, no? When we analyze BJT circuits, and this is one of them. Okay, nang nato ni memorize because these formulas are common to all types of BJT configurations. Kaya daghan man tag klase nga BJT configurations or BJT nga circuits, no? So daghan klase na siguro sa mga more than 10, no? But di man nato natanan gyud encounter. But there are daghan yun, no? So daghan og BJT configurations. Pero ang common denominator nila ang tanan is these four formulas. And the first of which is this one, no? IE is equal to IC plus IB. So again, please memorize this one. Kay permi na to ni gamiton. IE equals IC plus IB. And it's also noteworthy nga ang IC, especially when we're dealing with discrete transistors, nga ito lang ginagamit sa laboratory, are in the milliampere nga range, no? Same with IE. Nana permi sa milliampere nga range. So if makakuha tag mga answers nga integer values then amperes or microamperes then IC or IE. So let's try to check our circuit kung sakto ba gid ang atong kuan. So basta IC ug IE, milliamperes gid sila. And ang IB, very common for it to be in the microampere nga range. Okay? Microampere. So ang IE is milliampere, ang IC is milliampere, ang IB is nasa microampere, no? So if i-add na to ang milliampere ug microampere, usahay kung dako ra pud kayo ang difference, mahulog na si microampere is may mong negligible, no? Negligible na siya. Pwede ra i-ignore. So naay sub formula ani, pero careful lang ta kay ginagamit lang ni siya nga shorthand for switching applications. If mag-analyze tag amplifier applications, we should not use this formula, okay? Ato gid per me consider si IB. So shorthand lang ni siya for switching applications. Ako lang ni-erase karon. So it's good also to remember that IC is approximately equal to IE, no? For switching applications. Where IB is negligible. Okay? So tungod kay this na pala units, no? Pero again, for amplification applications, dili na to ignore si IB. Even if si IB is 1,000 times or 100 times smaller compared to IC or IE. Any questions so far, no, before I proceed?
Wash muna natin, ha?
Sabdan pa so far? The BJT as a node? Erase ako ng arrow. Okay, sige makapin eh. Okay pa so far, guys?
Yes, sir.
Okay. Thank you, man. So, sa PNP, the same gyapon, no? Even if ang direction sa current is reverse compared sa NPN, ang iyahang current relationship is pala ra gyapon. IE is IC plus IB ra gyapon, no? So, pasulod si IE, pagawa si IC, ug pagawa si IB. So, para actually, ma-learn na to soon na ang theoretical na analysis sa PNP ug NPN kung ato sang i-replace, no? Para di mag-matter. Ano lang siguro yung mga ginagmay nga kuan, mga unnoticeable na differences. So, dili ko first, balik ko sa previous na slide. In a normal operation, the base emitter is forward bias and the base collector is reverse bias. Okay. Before I go further, let's say we have this very simple circuit. No? This is just to put things into perspective. Okay? Load. Light bulb na lang, no? Light bulb. So, let's say, for example, muna itong switch. Okay? Conventional na mechanical switch. So, for us to turn on the light bulb, ato i-press ang switch. Okay? Press atong switch. Kung i-off nato light bulb, i-press nato ang switch. Okay? So, ano may tabo. Okay? Normal. Everyday na ginabuhat nato. But what if I want ng akong light bulb will only turn on kung naay, example, ay tao mo labay, no? Alarm ba siya kibali or anything, signifier na something na itabo. So, of course, I'm not going to use a sensor. I'm not going to use a mechanical switch. Okay, kinalaman siya i-manually turn on or off. What I'm going to use is a sensor, no? So, I need to use a sensor. But most sensors, almost all of them, in fact, even though two-terminal ang sensor, is dili-diretso makonect sa circuit. Okay? Whether sound sensor pa na siya, or light sensor, or any kind of sensor nga makadetect og physical nga measurements, dili na siya parehas sa mechanical, even if duha na siya ka terminal, dili na siya parehas sa mechanical switch nga i-connect lang nato diretso, no? Doesn't work like that. Okay? And usahay gani ang output signal sa sensor is naa sa mga microampere nga range gihapon ug mga microvolts nga range, no? So dili siya action, same like sa mechanical switch nga mo-connect din ni diretsyo for us to have a complete circuit. So what do? Din mo sulod si transistor. Okay? So isulod nato this transistor nato. NPN. Yan na. And mo ang input ni transistor is si sensor. Wala. Sa ground na siya. So si sensor ang mag-give og energy in the form of voltage or current kay transistor para maka-create na taog complete circuit, no? Or closed loop para musiga na dayon si light bulb, no? So simply speaking, that's what transistors do. Okay, that's what transistors do. They act as a switch if we are using sensors, no? So may ko dire. So how can we use the transistor as such? So na mga special nga rules. And here it is. In normal operation, the base emitter terminals should be forward biased and the base collector should be reverse biased. Tara. So nara ang base collector o base emitter, no? Again, and PNP yung gigamit nga transistor. PNP ni siya. Why? Because pasulod iyahang arrow. So kung asa ang arrow, mo na ang emitter. Kung asa ang horizontal line, mo na ang base. And base sakto, no? Yung yung collector. So sa tong rule, in the normal operation, dapat po nato ni i-qualify ning term nga normal, no? Si normal is not really that normal actually. Si normal here refers to the amplification nga function ni transistor. No? So this one is not a normal, no? Because the transistor here, the BJT, is used as switch. Nailahi nga rules sa proper nga term, dili man proper nga term ang pag-program, pag-operate, no? Na separate set of rules sa pag-operate kay BJT as switch. Pero to operate the BJT as an amplifier, which is its normal operation, the base emitter should be forward biased and the base collector is reverse biased. So, dapat naka-reverse bias ni dire and naka-forward bias ang base emitter. And kung amplifier ni siya nga application, ang pinaka-first ginato nga ginahinumduman, or ginapangita, is if indeed naka-forward bias sa base emitter. No? So, for us to know if naka-forward bias good si base emitter, we model this terminal right here as if na ay diode. No? As if na ay diode. And we want this diode to be forward bias. So sayop, no? Na forward bias or na reverse bias ang atong diode sa kani nga circuit.
Ma-reverse.
Reverse, diba? No? So sayop akong drawing. Okay? Reverse bias dapat ni. So dapat igana. Okay? Yeah, so in this case, naka-forward bias na siya. PNP, manggod ni. So, again, anaman ko ganiya nga, usually na ito ginagamit is NPN. Para sa NPN, iyan ang atong diode. Kaya dapat naka-forward bias. No? So, dili manoon all the time nga need na to mag-draw og diode diha. No? Pero karon na ni siya kay kinahanglan na ko explain. No? So, as if nanay diode diha. Okay? So, either sensor ni dire or pwede gihapon signal source, amplifier man din no? So, dili siya sensor. Signal source siya. Okay? So, so in this case, naka-forward bias ang atong diode. And if naka-forward bias ang atong diode, atong virtual diode, na siya yung voltage drop na 0.7 volts. No? So that's the second relationship that we need to always take note of. For the BJT to be used as an amplifier, VBE, or the voltage across the base and emitter terminal, will always be 0.7 volts. Okay? So, please remember this one. So far, these two, IE is equal to IC plus IB, and VBE is equal to 0.7. Sabi po niyo? For the NPN type, not shown, the collector is more positive than the base, which is more positive than the emitter. For the PNP type shown, the voltage are reversed to maintain the forward bias, a forward reverse bias. So don't worry if medyo vague pa as of this time ang most of the things that I'm talking about. This will all be made clear if mag-start na tao analyze og actual amplifier circuits, no? So pwede mangod even kanino kaning mga technical naman nga mga information. It's possible na di dahil natin ni ma-absorb right here, right now. Kanilang, no? Kaning mga formula lang. Okay, if ma-memorize natin nga mga formula, ma-derive man nato diha ang iyang operation, no? So far, ito lang sa next. Hapo mo tayo two others, no? So, inom duman sa to, ha?
It's yours?
Yeah.
You have money?
Sige, next. This one. The BJT characteristic curve. The VI relationship of the
You do not have money, man. Where?
not just the plain na VI. Kaya daghang matag V ug I nga isgutan when we speak of transistors. Unlike the diode that only has VD and ID. And mo ang characteristic curve sa atong diode. Right?
Did you see?
As for the BJT, natay tulo ka pair, no? Nga currents o voltages. But not all of them atog yung i-cover. Okay, some of them are just trivial. No? Pero nagyapon. Ang ato lang i-cover is one pair of these voltages and currents. So the three currents are those three na ito na mentioned earlier, IC, IE, and IB. Napuntay voltage VCB, voltage VBE, which is equal to 0.7 always, if we want to use it as an amplifier, and voltage VCE. So sa ato pag-analyze og circuit, kaning tulo, almost always, pangitaunon. Okay, si IC, IE, ug IB. Si VBE, no need to solve. Kaya memorize na siya. Si VCB is trivial because remember, in the normal amplification nga operation, the collector base is reverse bias. No? So, dili na to need nga pangitaon si VCB, but only VCE. No? So, kaning upat, muna itong ginasolve sila. No? For analysis na problems. For design problems, maybe given ni sila and baliktad ang mga resistors ang pangitaon. So this is a sample characteristic curve of VCE versus IC. VCE versus IC characteristic curve. Napoy other characteristic curves sa other parameters, other V versus I parameters. So mostly again atong gamiton is VCE versus IC nga characteristic curves. So it has three parts. Upat kay ni nga part dapat, no? May kulang isa nga part wala na butang. The first part is the active region. So active region. Mostly measured na siya or located na siya dire. No? The majority nga portion sa characteristic curve is the active region. No? So if we want our amplifier to be operating as an amplifier and magdoman tag line ani, we call that line the load line. No? Magdoman lugar tag load line. Later na ako explain nung sa gid ni pero it somehow looks like this, no? And if the intersection of the curve and the line falls inside the active region, indeed, the BJT acts as an amplifier. So in this case, intersection sa curve ug sa line is this one. Oh? So, muna itong line, muna itong curve, ang intersection. Okay? So, ang intersection is naman sa sulod sa active region. So, the amplifier acts, the BJT acts as an amplifier. Okay? So, erase na ako ni. That's the first region of importance sa characteristic curve. Another region of importance is the saturation region. Asa mo kitang saturation region? Here. Here. So, if ang atong load line falls somewhere inside the saturation region, let's say for example, kani ang atong load line, dala ang atong intersection. So, our BJT does not act as an amplifier na. Kaya naman sasulod sa saturation region ang intersection. So, the saturation region is characterized by these properties. No? In the saturation region, current is maximum. Okay? And voltage is 0 or minimum, no? Minimum, sometimes 0. So, dahil nato ni madumduman, because when we say saturate, diba, it's like a saturated na sponge full of water. So, the transistor now is full of current. Okay? Full of current. So, maximum yung amount of current. Ang partner sa saturation region, nga wala nakabutang dire, I don't know why, should be the cut-off region. If ang saturation region is to the left of the active region, the cut-off region is below. Below the active region. And it's characterized by the inverse properties sa saturation region. IC is 0 and VCE is maximum. Okay? Notice, asa mo nag-fall ang cut-off region? Di ba sa horizontal axis? And when we say horizontal axis, dili ba y is equal to 0 or IC is equal to 0? And VCE is maximum. The same gyapon sa saturation region. Saturation region falls within the vertical y-axis. And if kung vertical y-axis, 0 ang x or 0 si VCE and maximum si IC. So, dali lang mahinumduman, no? Dali lang mahinumduman ang properties sa both ni saturation region and cutoff region. While in fact, saturation region and cutoff regions are used simultaneously, no? Partner ni silang duha. If indeed partner ni silang duha, what device acts as a combination of a BJT operating in saturation and cutoff region? Unsa ni siya nga operation? Unsa nga device ni? Mala siya mag-change siya from one state to another. Unsa nga device? Very simple device.
Oscillator.
No, dili oscillator, Although we could create oscillators using BJT, pero no, dili na siya oscillator nga kuan operation. Simple lagi kayo nga device. We've covered this extensively from the previous meetings.
Diode.
Yes, diba? Diode or switch. Mala siya switch, right? And the diode, of course, acts as a switch. Kung naka-cut off, mara siya diode nga off. And kung saturation, mara siya diode nga on. Diba? Remember, if the diode is forward biased, or siya og shorted nga switch, diba? Here, current is maximum and voltage is 0. Whereas, if naka-reverse bias itong diode, open circuit, current is 0, yet voltage is maximum. Or in this case, the supply voltage. No? So if we want, as a reminder, if we want our BJT to act as an amplifier, we use it in an active region. No? BJT as amplifier. But if we want our BJT as a switch, we operate it in the both the saturation and the cutoff region. So ito akong example earlier, dala, this BJT is both operating simultaneously in the saturation region and cutoff region. If there's signal in the sensor, isaturate niya ang switch. If there's no signal from the sensor, i-cut off niya ang switch or ang BJT. No? So, kana. Actually, those are the three most important regions of operation of our BJT. The other one is the breakdown region. If ang atong transistor reaches this region, the white smoke will come out of our transistor. So, mababa na siya. So, it's always important to check if na-reach ba ang breakdown region or wala. How? By just plain multiplication of IC and VCE. Na. If wala pa na-reach, okay lang. Meaning na pa siya sa active region. Okay? Next slide. BJT characteristic curve. Yeah. Each of these curves represent only one. No? Isa lang man na ani ang atong magamit sa at an instant. No? Dili man nun tanan. Okay? So if our IB, let's say for example, our IB is 3 microamperes, 3 microamperes, kanilang na characteristic curve atong gamiton. Ignore na dahil natong uban. No? Kana lang. So, di na to na siya i-mind, dili na to siya i-mind. Because at any instance, isa lang po nga value of IB atong gamiton. No? So, kana atong i-take note lang, and then when we draw a load line, kana, nasa ilang intersection, mo to ang atong mga operating points. So, how do we, karoon na ba nga slide dapat na ni i-reveal? How do we define our circuit? Sige, dili lang siguro. Kanina nga circuit. Kanina lang nga characteristic curve. So, based ani nga characteristic curve, how do we draw our load line? First is, of course, we'll determine pila ang atong base current. No? So, we choose any of these three. Any of these choices. 6 choices man sa kanila nga example. Although, daghan pa man yung klase nga combinations. No? So, let's say for example, by atong example kanina, we'll choose 3 microamperes. So, we'll use this characteristic curve. No? This one. And then, we'll plot our points. I-plot na to ang points sa atong supply voltage here. No? Supply voltage. For example, our supply voltage is 15 volts. So this here is 15 volts. Ang ato i-plot sa y-axis or sa IC axis is ang value ni IC saturation, no? Or the maximum value for IC. IC saturation. Yan na. And i-connect lang natong duha, no? Okay, I hope masakto na ako. O connect ang duha. Timing. No? So malaging ana. And asa ilahang intersection, dire, atong i-project siya sa x-axis o sa y-axis. Kung asa mo fall, mo na ang value sa atong BCE. O sa y-axis, mo ang value ni IC. Although it sounds simple, it's difficult to do because dili man accurate, no? Kung magsilang tao gamit sa characteristic curve, especially if ang atong value sa IB is wala dire, no? Example, kani defined man 2 microamperes, 3 microamperes, 4 microamperes. What if ang akong gamiton is 3.5 microamperes, then wala dili available. So maglisod tao gamit og characteristic curve. Ako lang nag-i-introduce dire para ang concepts is dili mo mag-follow, no? Dili mag-follow ang concepts. Pero kung mag-analyze ng tawag circuits, we'll do a more theoretical na or analytical na method, no? Solving, no? Solving. Masolve man Masolve Masolve pod Okay? So we do not need to use all the time the characteristic curve. Pwede lang siguro pang check, no? Check na to itong mga values, kung asa ba dire, no? Kung sakto ba akong nakuha ng mga parameters after analysis, after computation. Pero dili nato norm nga gamiton ang characteristic curve for analysis. For checking maybe, no? So the collector characteristic curve illustrates the relationship of the three transistor currents. By setting up the other values of the base current, a family of collector curves is developed. So we have now a relationship of IB and IC. We call that one beta. Beta is the ratio of the collector current and the base current. So lahi ni nga name. Sometimes they call this one amplification factor, no, or gain, no. Amplification factor of the BJT or its gain, no, and many other terms. We could call it as plainly as this one, beta. Other specification sheets call this as HFE. HFE. I don't know why HFE ang gigamit, but I know why H ang letter nga pag nag-choose because ang kalaan nga model sa pag na ginagamit before sa pag-model sa BJT is ang H model, no? H parameters, I mean. H parameters model. No? So silang di na important for us to know right now. Don't worry about it lang. So B, beta DC, or plainly beta is equal to IC over IB. Or rearranging, IC is equal to beta IB. And this is relationship number 3. Again, try to memorize this one. Pero mi na ito nigamiton. IC is equal to IB is equal to beta IB. Mas dali na ko ninomdomon because permi tapad si beta o si B. No? So IC is equal to beta IB. It can be read from the curves, however, that the values of beta is nearly the same wherever it is read. No? Sakto man. No? Maski paasaan niyo itong gamiton, same lang beta. So combining relationship number 3 and relationship number 1 before, no? We could establish relationship number 4. If IE is equal to IB plus IC and IC is equal to beta IB, IE then is equal to IB plus beta IB. Or factoring out IB, IE is beta plus 1 IB. Relationship number 4. And these 4 formulas are the ones that we will always be using and dapat memorize ko na to, kaning upat. Starting with these 2. No? IE equals IC plus IB. VBE is 0.7. IC is beta IB. And IE is beta plus 1 IB. No? So, memorize na daan. Example. What is the beta for the transistor shown? What is the transistor that we use? 30 microamperes. What to siyang i-project? What level is this? Sa mga 5. Yeah, thank you. 5 milliamperes. So, dividing 5 divided by 30 microamperes, take note. Micro si 30. Pila ba ni? 167. And beta is unitless. Okay? Because again, beta is a factor, amplification factor, or gain. So, no units. 167 lang. It's also noteworthy that beta falls somewhere in between 50 and 400. Normally, nasa mangyaning range ang beta. It's normal for us to see beta equal to 50 or beta equal to 400. Naman akong ingon earlier, cut off. Saturation, no? Both the saturation and cut off are used in tandem. No? So, off, on, off, on. Voltage is minimum, approximately equal to 0.2 or pwede na ito i-approximate as 0 gyud. No? The current is, the saturation current is maximum. No? Or is maximum. Collector, collector current, yeah, maximum. Whereas sa cutoff, no base current resulting in, di ba, in the cutoff region, there is no base current. Okay? So, IB is equal to 0. And because IC is beta IB, and IB is 0, it goes that IC is also 0. No? So, mo man nga way nga ma-cut off na to ang atong transistor because ang atong sensor dili ka produce og voltage. Og current, So, which results only an extremely small leakage current. Di lang kayo na to na-explain in detail ang leakage current tungod man sa mga minority carrier flow. Pero we could say that at cut-off, IC is equal to 0. Yeah. So I hope that's clear. No? Saturation on, cut-off, off. Off, on. Active region, amplifier. Okay? Di naman itong DC load line, represents the circuit that is external to the transistor. Ako na-explain kanina, di ba? It's done by connecting the saturation points, IC sat, and the cutoff point. Where the cutoff point is when the voltage is equal to the voltage source. No? Kaya muna ako explain kanina. So this is an example. No? So pag-solve sa saturation current o cutoff voltage. Cutoff voltage is equal to voltage source is equal to 15 volts. No? Before I go further, reminder lang din wala na ako na point out earlier. Kung may yung tag VCE, VCB, and VBE, these are voltage across terminals. Okay? Voltage across terminals. Whenever we read these voltages, VCC, VBB, and VEE, these always pertain to supply voltages. Supply gina sila Fermi. No? So, same right here, VCC is 15 volts. Because VCC is the supply voltage. If i-connect na to dire sa emitter, let's say for example mag-connect ta dire og voltage source gihapon, we designate that as VEE. Same here. Ang supply current no, sa base, VBB. Ang currents is IC, IB, IE ra gyud. No? Walay ICE, walay ICB, walay ICE. Walay ICC, walay IEE o IBB. Sa voltages na sila. So this is an example of a data sheet for a BJT. Dalade HFE. Pagyapon ang ginagamit nga term karon for beta sa mga specification sheet. So for the 2N3904, it has a maximum beta of 300 and minimum beta of 100. Okay. So I guess that's it. Lupad eh. Tabi ko na ni. Summary. The BJT amplifier. The BJT operating in the active region. No? Again. A BJT amplifies AC signal by converting some of the DC power from the power supplies to AC signal power. An AC signal at the input is superimposed in the DC bias by the capacitive coupling, and the output AC signal is inverted and rides on a DC level of VCE. So what happens here is, if natay signal source here, say for example kana sorry. No. So this is IB. Remember, IC is beta IB. So it will increase, IC will increase by a factor of beta. No? So magdako siya. No? Compare ani. Hindi nga na. No? But aside sa na amplify siya. Ang buhaton pag sa transistor na circuit is aside sa pag-amplify, iyahang i-raise to a specific DC level. Or yung i-clamp, di ba? I-clamp. Remember this before because a diode could be used as a clamper. No? So, na-clamp siya to a specific DC level. No? I think VCC man siguro. No? At the value of VCC, if I'm not mistaken. VCE di ay. Wala, VCE. VCE. And dili lang kay iyahang gi-amplify and gi-clamp. Last niya nga buhaton sa signal. Mao gini ang effect sa BJT, no? Wala na kita mabuhat ani. I-inverse niya. Invert. No? So this is now the final output of our ICE. IC, no? Conceptually speaking. Ang total and final nga output. So ang input signal is yung i-amplify, i-clamp, and i-inverse. Yan na. So, dire is given input and final output naman. No? So, wala niya gi-display dire ang unsang may tabo in between. Ang pag-amplify ug ang pag-amplify ug ang pag-clamp. And last is ang pag-inverse. Ano? So, ang wisdom here is we should choose an appropriate value for VCE. Okay? I-design na to ang circuit as such na ang VCE is high enough para ma-accommodate ang negative half cycle sa atong signal. Diba? Kaya kung ubos-ubos ang value sa VCE, no? Example, nalang lugar dili ang VCE, pero mo na yung atong signal, so ma-clip off na siya. So sayang. So we should choose appropriate values for our resistors for our VCE to be high enough to accommodate the negative half cycle of our signal. Yan na. The BJT has a switch. Kung cut off, 0 ang applied voltage sa base or VBB is equal to 0. O saturation, na. Okay. Na. But should be high enough to saturate the collector current. Okay, I guess that's it. Kaning nga slide is different man sa PCAS. Kanigid ang slide ni Boiler Stud. Pero mas ganahan ko atong previous kay mas visual. No? So, di na ako na-cover kay palalaman na sa ganina. Ako lang noon gibutang dire for additional information. So far, any questions? I guess we'll end here this afternoon. We'll continue.
Katong sa beta, sir ba?
Saan sa to?
Katong sa beta, sir ba? Di ba naman to
Beta,
yung
oo.
na
Okay.
50 to 400?
Oo.
Kung muubos sa 50, sir, or malapas 400, does that mean na mali ang solution or sometimes may tabo na?
Malagi nga na siguro kuan. Kasi nag-ask si
Dan, sir.
Dan.
Dan.
Si Dan.
Yes,
Okay.
sir.
Yeah, yes, Dan. Kuan ta ka ng if sa atong computation mo gawas nga ana isa na nga indication nga, uy, basig na ako yung wrong
Mali.
sa akong kuan. Oh, mali.
Sige.
Especially dire, asa to? Especially dire, nag-mark na ba siya daan nga 100 to 300, di ba? If kani nga pyesa itong gamiton. So, mga kuan na siya, mga indications na siya na maybe na something wrong sa akong circuit. Or para safe, pwede na ako i-design ng akong circuit nga ang beta is 250. Yan na. Yan na siguro done. Oo. So,
Yes, sir. Thank you, sir.
tsada imong kuan, nice imong observation, imong question, I mean. Bitaw, any more questions? If medyo hazy pa now, that's okay. That's normal. First pumato ni nga run sa BJT. Mas ma-make clear ang things when we try to analyze na soon og mga amplifier circuits. Unconsciously ma-review na to ni, no? Kaning mga kuan, kaning mga concepts unconsciously ma-review na to ni as we try to analyze amplifier circuits. So, atong kuan lang gid karon, take away, if there's something we should always remember, sugod karon, is to memorize those four relationships or formulas for PJT. Katulang sa gyud upat, no? Bahala kaning mga theoretical dire nga kuan, nga mga concepts, no? Pwede naman yun i-review ang slides or pwede naman po ninyo i-review ang atong recorded na kuan na video. Anytime pwede naman review. So pwede lang gid siya malimtan, no? Pero ayon niyo kalimta kaning upat, no? Starting with these two and these next two. Kana, no? So kana lang. Any more questions?
What's that? Oh, it's
None, sir.